heart of the Andromeda Galaxy lies a hidden giant, a supermassive black hole known as M31's central engine, weighing millions of times more than the Sun. Its gravity shapes the motions of stars, stirs gas into violent orbits, and quietly sculpts the future of an entire galaxy. Today, we journey into the core of Andromeda to explore what makes this cosmic monster so powerful and what it can reveal about the fate of galaxies like our own. If you enjoy calm trips to the most extreme places in the universe, please like, subscribe, and share, and tell us in the comments what you would ask about the supermassive black hole at Andromeda's core. Thank you for watching. Now let's begin. In the quiet part of the nearby universe, a small collection of galaxies known as the Local Group moves under shared gravity. This group contains the Milky Way, Andromeda Galaxy, also called Messier 31, the Triangulum Galaxy, and many smaller systems. Each galaxy carries its own history of star birth, gas clouds, and dark matter, but together they form a bound structure that stays tied by gravity over very long times. Within this larger arrangement, the Andromeda Galaxy stands out as the most massive member, or close to it, and its center becomes an important place for studying how a very heavy black hole can sit inside a galaxy-scale system. From the vantage of modern observatories, the Andromeda Galaxy appears as a large spiral with a bright central region and extended arms of stars and dust. It lies at a distance of about 2.5 million light-years, close enough on cosmic scales that telescopes can separate many individual stars, yet far enough that the whole galaxy still fits into a single wide-field view. This combination of distance and clarity makes Andromeda a useful target for understanding the link between a galaxy and the black hole at its core. Astronomers see that many large galaxies host supermassive black holes at their centers, with masses ranging from millions to billions of times the mass of the Sun. The Andromeda Galaxy, being both large and nearby, naturally falls into this picture. Its central region shows signs of strong gravity and compact structure, placing it among the important targets for careful study of a central black hole in a fairly normal galactic environment. The local group context matters because the motions of galaxies within the group suggest how much mass each system carries, both in stars and in unseen dark matter. The Andromeda Galaxy and the Milky Way move toward each other under mutual gravity, and this motion is measured through small shifts in the light of their stars. These shifts, known as Doppler shifts, show that Andromeda approaches the Milky Way rather than receding. That approach implies a deep gravitational well around the Andromeda Galaxy, supported by large amounts of matter spread from its outskirts down to its center. In this setting, a central black hole is not an isolated object, but part of the full mass budget that holds stars, gas, and dark matter together in the inner region. Within the local group, the Andromeda Galaxy also has many satellite galaxies that trace the reach of its gravity. Their orbits and overall distribution give clues about how masses spread in the halo and disk of Andromeda. When astronomers model these orbits, they find that a large fraction of the mass is not in visible stars, but in a more extended component that does not emit light. Even so, the models also require a dense central concentration of mass to match observations in the inner parts of the galaxy. This need for a compact center is one of the reasons the core of Andromeda remains a central focus of research. The local group environment further helps by offering several points of comparison. The Milky Way is believed to host a supermassive black hole at its center, and observations support this with precise measurements of stellar motions near the galactic core. By comparing the Milky Way and the Andromeda Galaxy, Astronomers can ask whether galaxies of similar overall mass tend to host central black holes of similar mass, or whether the details of their growth and merger history lead to different central outcomes. The Triangulum galaxy adds a smaller companion to this comparison, set with its own nuclear properties that can be weighed against those of Andromeda. Because these galaxies are near each other in space, they share a similar large-scale environment, which reduces some sources of uncertainty when differences in their centers are studied. The local group is also quiet in the sense that there are no very large clusters nearby with many tens or hundreds of massive galaxies. Instead, there is a small number of main galaxies with surrounding dwarf companions. This quieter setting allows a clearer reading of how internal processes such as star formation, gas inflow, and central black hole growth operate over long times without the strong external disturbances common in crowded clusters. The Andromeda galaxy, in this context, offers an example of a massive spiral galaxy whose center can be examined in detail without strong interference from neighboring giant systems. From the local group perspective, the Andromeda galaxy is a system whose total mass influences the motions of its neighbors and whose center contains a compact object that adds to this mass in a concentrated way. When astronomers simulate the evolution of the local group, they include the total mass of Andromeda as a key quantity, and the presence of a heavy central black hole is part of this total. Although the black hole itself occupies a tiny volume compared with the galaxy, its mass is large enough that it has a measurable effect on the motions of stars and gas very near the center. Modern observatories support this work by providing images and spectra of the Andromeda galaxy across a wide range of wavelengths. Optical telescopes resolve individual stars in the outskirts and inner regions. Radio instruments trace gas in cold clouds on large scales, and infrared observatories help to see through dust toward the center. Together, these tools allow astronomers to link the large-scale role of Andromeda within the local group to the detailed behavior of matter close to the center. In this way, the local group view supplies a stable framework in which the central black hole of the Andromeda galaxy can be studied as both a local source of strong gravity and a small but important part of the total mass of its host galaxy. This broader context guides the questions that are asked about the Andromeda black hole and shapes how new measurements of its surrounding stars and gas are interpreted. The Andromeda galaxy presents a clear overall structure that helps show why a strong central mass is needed to keep its inner regions in order. Seen in optical light, it appears as a large spiral system with a wide, thin disk, bright spiral arms, a central bulge, and a faint extended halo. The disk contains most of the visible stars, arranged in a flattened shape that stretches far from the center. Within this disk, spiral patterns mark regions where gas and stars are somewhat more concentrated. Dust lanes thread through these arms, partly blocking the light of stars behind them and outlining the structure of the disk. At the center of the disk lies the bulge, a rounder and thicker region of older stars whose light rises smoothly toward the nucleus. Together, disk, arms, and bulge make up the main luminous body of Andromeda. Surrounding this is a much larger halo that holds old stars, globular clusters, and a dominant dark matter component. When astronomers examine the way matter is arranged from the halo down to the bulge, they find that the Andromeda galaxy behaves like a system controlled by gravity. On every scale, the halo extends far beyond the visible disk and is thought to contain most of the galaxy's total mass in the form of dark matter. This extended mass helps explain why stars in the outer disk move at nearly steady speeds, instead of slowing down with distance from the center. The disk itself, filled with stars and gas, lies within this greater halo and feels its pull. However, as the view moves inward, the pattern of light and motion points toward a central concentration that cannot be explained by the halo alone. The bulge is the first sign of this central buildup. In the bulge, stars crowd together and the surface brightness climbs toward the nucleus. The shape of the bulge, which is more spherical or slightly flattened compared with a disk, suggests that stars there move in orbits that are less ordered than the nearly circular paths in the outer disk. Instead of following simple rotation around the galaxy's axis, many stars in the bulge follow more complex paths that loop through the central region. This mixture of orbits still reflects an overall gravitational pull that becomes stronger closer to the center. The steep rise in brightness indicates that a large amount of stellar mass is packed into a small central volume. Yet when the total visible mass of stars in the bulge is estimated from its light, and the predicted gravitational field is compared with what is inferred from stellar motions, the visible stars do not fully account for the depth of the central potential well. This gap between visible mass and measured gravity in the innermost part of the galaxy points toward an additional compact source of mass. The large-scale arrangement of stars and gas in Andromeda also shows that the galaxy is dynamically settled rather than strongly disrupted. The disk is relatively regular, with spiral arms that can be traced over wide angles, and the bulge sits centrally within this rotating structure. There are signs of past interactions and streams in the outer halo, but the inner galaxy remains coherent. This regularity suggests that any very massive object at the center has been present for a long time and is an integral part of the system's balance, not a recent addition. A central mass that is both very heavy and very compact fits naturally into this picture because it can influence motions within the inner region without disturbing the overall order of the larger disk and halo. The gas component of the galaxy adds another piece of information. Neutral hydrogen gas traces the outer disk and outlines the rotation pattern of Andromeda on large scales, while molecular gas concentrates more toward the inner regions, where densities are higher. The distribution of this gas follows the underlying gravitational field, piling up where orbits and density waves slow it down. Near the center, gas is drawn into more tightly bound orbits, and some of it settles into rings or lanes that circle the nucleus. The fact that such structures persist and do not quickly collapse suggests an organizing central gravitational source that is very concentrated but stable over long time scales. In a galaxy like Andromeda, a very massive black hole offers a natural way to provide this central pull. The extended halo and disk explain much of the behavior of stars and gas at large in intermediate radii, while the bulge explains a further increase in density closer in. Yet the innermost region, where light rises sharply and orbital speeds become high over short distances, calls for a concentrated core that cannot be built from stars alone without conflicting with other observations, such as the way light is distributed and the way stars would interact if the density of normal matter became too extreme. A supermassive black hole with mass equivalent to many millions of suns, confined to a region no larger than the inner part of the solar system, can supply the needed gravity without producing additional light. Its presence fits with the general pattern seen in many galaxies of similar or larger size. The global structure of Andromeda, therefore, does more than show a beautiful spiral form. It provides a set of boundary conditions for any model of the galaxy that aims to describe the central region. The halo sets the broad mass scale. The disk and arms show how matter rotates on large scales, and the bulge reveals how mass density rises toward the center. When these pieces are combined, they point toward a requirement for a very compact and heavy central object. In this way, the overall structure of the Andromeda Galaxy frames the search for its central black hole, indicating that such a massive core is not an extra feature, but an expected part of the gravitational design that holds the inner galaxy together. The rotation of stars and gas in the Andromeda Galaxy provides one of the clearer sets of measurements that point toward a deep central region of gravity. When astronomers map how fast material moves around the center at different distances, they build what is called a rotation curve, a record of orbital speed as a function of radius in the disk. In a simple system where most of the mass lies close to the center, orbital speed would rise near the middle and then decline as distance increases, in a way similar to planets in the outer parts of a planetary system that travel more slowly than those closer in. Instead, in the Andromeda Galaxy, as in many large spiral galaxies, the rotation curve rises in the inner regions and then stays nearly flat, or only gently changes over a very wide range of radii. This behavior shows that mass is not concentrated only in the bright central bulge, but is spread through an extended halo. The flat part of the rotation curve points to the presence of dark matter, which doesn't radiate light yet contributes to the gravitational pull that holds fast-moving outer stars and gas in orbit. However, the inner rise of the rotation curve, where speeds increase over relatively short distances toward the center, carries separate information about the central regions and the likely presence of a very compact mass. In the outer disk of Andromeda, neutral hydrogen gas serves as an effective tracer of rotation. Radio observations detect the emission of this gas and measure how its frequency shifts due to motion along the line of sight. From these shifts, astronomers infer orbital speeds at various distances from the center. The pattern that emerges shows that stars and gas in the outer parts move at speeds that remain roughly constant with radius rather than falling off, which agrees with a large extended dark matter halo. As the view moves inward, optical and infrared observations follow stars and ionized gas in regions where neutral hydrogen is less dominant. These inner measurements show a steady climb in orbital speeds as the radius decreases. The gradient of this inner rise reflects how quickly gravity strengthens toward the center. By comparing the observed rotation pattern with models of how gravity should behave for different mass distributions, astronomers can ask how much of the inner pull is supplied by the stellar bulge and how much must come from an additional compact source. When they use the measured light to estimate the mass of stars in the bulge and disk, they find that stellar mass alone does not fully explain the steepness of the central rotation rise. A reasonable amount of dark matter in the inner region is also included in such models, but even then, the fit to the observed speeds often improves significantly when a central point-like mass is added. In practice, this central mass is not treated as a perfect mathematical point, but its physical size is small compared with the scale of the galactic bulge, so it affects orbits in a way that closely resembles that of a compact source. In the case of Andromeda, the mass needed in the very center, inferred from rotation and other dynamical data, reaches many millions of times the mass of the Sun. Such a mass cannot be made of ordinary stars crowded into a tiny volume without leading to conditions that would make the system unstable. Collisions and close encounters would cause stars to merge, disrupt, or be ejected over relatively short astronomical times if they were packed so densely. This reasoning supports the idea that the central mass is instead a supermassive black hole that can hold a large amount of mass in a very small region, defined by its event horizon, while maintaining a long-term stable influence on surrounding orbit. The rotation data do not show the black hole directly because the region where its gravity dominates has a very small angular size from Earth. Still, rotation measurements at the smallest radii that can be resolved help set the scale of the central mass by showing how fast stars and gas move just outside this unresolved domain. In the innermost measurable parts of the disk and bulge, orbital periods shrink and velocities become high compared with more distant regions. The smooth continuation of the rotation curve into these inner zones, together with more detailed stellar velocity studies in the central bulge, supports a picture in which a massive but compact object sits at the very center and ties the observed motions together. Rotation patterns also show that the Andromeda galaxy is not a system where random motions dominate on large scales. Instead, much of the mass in the disk follows nearly circular or slightly elliptical paths around a common center. This ordered motion allows dynamical models to be built with some confidence because the equations describing rotation in a gravitational field are well understood in the context of Newtonian gravity. And closer in, general relativity. The agreement between these models and the observed rotation curve across a wide span of radii gives a consistent view of the galaxy as a collection of stars, gas, dark matter, and a central black hole arranged in a way that fits the measured speed. Another important aspect of the rotation pattern is its symmetry. When observers measure velocities on opposite sides of the galaxy along the major axis of the disk, they see that speeds match well once corrected for the tilt of the disk with respect to the line of sight. This symmetry indicates that the galaxy is not strongly disturbed by recent major mergers in its inner parts, and that the mass distribution is roughly axis symmetric. A central black hole embedded in a regular bulge and disk naturally fits into such an axis symmetric model, acting as a small but dense addition at the center rather than as an off-center or transient feature. The stable ordered rotation around the nucleus over long times helps the central black hole maintain its position at the dynamical center of the galaxy. The inner portion of the rotation curve, where the influence of the bulge and central mass is strongest, offers a transition region between the halo-dominated outer parts and the black hole-dominated very inner domain. By carefully fitting this transition with models that include a bulge, disk, halo, and central compact mass, astronomers refine their estimates of how much mass lies in each component. In these fits, the central mass that best matches the observations corresponds to a supermassive black hole, whose gravity becomes dominant over that of individual stars, only within a relatively small radius. Outside that radius, the combined pull of many stars and dark matter takes over, but the effect of the black hole is still present in the way orbits are arranged near the center. In this way, the rotation curve, though largely shaped by the halo and disk on large scales, also carries in its inner rise and detailed form clear quantitative information about the depth of gravity at the core of the Andromeda galaxy and the need for a very massive central black hole to account for what is observed. The central bulge of the Andromeda galaxy offers a more detailed look at how gravity strengthens toward the nucleus and how stars respond to this pull. The bulge is a rounded, bright region of mostly older stars that sits at the center of the disk. Its light does not come from a flat layer, but from a three-dimensional swarm of stars, whose orbits fill a thick central volume. When astronomers map the brightness of the bulge, they find that surface brightness rises steadily toward the center, which means more and more stellar light is packed into smaller and smaller projected areas. From this change in brightness with radius, they infer how stellar density, and therefore stellar mass, and creases toward the core. The bulge alone already represents a significant concentration of mass compared with the disk, yet careful measurements of the motions of bulge stars reveal that the pull of gravity grows even faster than the light alone would suggest as one approaches the innermost region. To measure these motions, astronomers use spectra, which separate starlight into its component colors. Each star has characteristic absorption features in its spectrum. Where many stars are blended together in the bulge, these features broaden, shift, and take on shapes that reflect the range of velocities along the line of sight. The overall spread in velocities, called the velocity dispersion, is a statistical measure of how far stars move in many directions, rather than in a single ordered rotation. In the outer parts of the bulge, the velocity dispersion has a certain value that reflects the average depth of the gravitational potential there. As one looks closer to the center, this dispersion increases, showing that stars in the inner bulge move faster on average and feel a stronger gravitational field. By mapping how this velocity dispersion changes with distance from the center, astronomers can test models in which the mass that creates the gravitational field is distributed in different ways. If stars in the bulge were the only source of mass in the inner region, then the distribution of light, together with a reasonable assumption about the mass carried by each unit of starlight, would predict a specific pattern of stellar speeds. When such a model is compared with observations in the Andromeda bulge, it explains the motions fairly well at intermediate radii, but falls short in the inner few light years. In these innermost zones, the observed velocities rise more steeply than the starlight alone can support, even when a range of possible mass-to-light ratios is explored within plausible limits. This mismatch suggests that an additional mass component is present, one that is much more concentrated than the bulge stars themselves. Another way to look at the bulge is through the mix of rotation and random motions. In some bulges, stars rotate significantly and also show random movements. In others, random motions dominate. In Andromeda, both rotation and dispersion are present, but the dispersion becomes particularly strong. Near the center, astronomers model this behavior using equations that connect the distribution of stars, their average velocities, and the gravitational potential. These are known as dynamical models, and often assume that the bulge is approximately symmetric around the rotation axis. When a compact central mass is included in such a model, the predicted rise in velocity dispersion and the detailed shape of the absorption lines in the central spectra match the observations much better than when no central mass is present. This improvement is not just qualitative but quantitative, as the best-fitting models point to a central mass of many millions of solar masses concentrated on scales smaller than the region that can be directly resolved. The data also show that the line-of-sight velocities in the central bulge region are not simply the extension of the disk rotation pattern. Instead, the bulge stars follow more complex orbits that pass near the center and feel the combined pull of the bulge, the disk, the dark matter halo, and the central compact object. The fact that velocity dispersion rises toward the center in a smooth fashion rather than in a chaotic or irregular way suggests that the central mass has been part of the structure for a long time, and that stars have had time to settle into orbits that are consistent with a stable gravitational field. This long-term stability is more easily achieved if the central mass is a single, massive black hole rather than a cluster of many smaller compact objects that might interact strongly. If the extra central mass were made of ordinary stars or stellar remnants packed into a tiny region, their mutual gravity would lead to frequent close encounters and collision. Over cosmic times, these interactions would change the structure of the cluster, possibly causing it to expand or eject stars, which would alter the observed kinematics and brightness profile. Observations of the Andromeda bulge instead show a central region whose kinematic and photometric properties appear consistent with a smoother, more permanent concentration of mass. This is one of the reasons why a single supermassive black hole with mass far above that of any star is a preferred explanation. The increased speeds toward the center also mark the transition between regions where the combined pull of many stars dominates and regions where the gravity of the central mass becomes important. Astronomers sometimes speak of a sphere of influence of a black hole, defined as the radius within which the gravitational field of the black hole outweighs that of the surrounding stars. In practice, this sphere is not directly imaged in Andromeda, but its scale can be inferred from the behavior of stellar velocities. The radius where the dispersion and rotation patterns begin to deviate strongly from what the bulge alone can account for gives an estimate of how far the central mass reaches in dynamical terms. For the Andromeda galaxy, the sphere has a size measured in only a few light years, which is small compared with the overall bulge, but still large enough that its signature can be detected by precise spectroscopic observation. Technological advances in telescopes and instruments, including high-resolution imaging and spectroscopy, have been essential for these studies. Ground-based observatories with large mirrors and adaptive optic systems can correct for some of the blurring caused by Earth's atmosphere, while space telescopes avoid atmospheric effects altogether. Both kinds of instruments have been used to obtain sharp views and detailed spectra of the Andromeda bulge. With these tools, astronomers can place small apertures on the sky that sample light from regions close to the center and measure how absorption lines behave there. The resulting velocity fields, when combined into two-dimensional maps, reveal how stars move not just along a single axis, but across the central area. These maps show that the inner bulge is dynamically hot, with high random speeds that rise as the radius decreases. When such observational maps are compared with predictions from models that include or exclude a central black hole, the version with a supermassive black hole provides a better match to both the magnitude and the spatial variation of the velocity. The picture that emerges from the bulge is therefore one in which stars act as test particles that feel the global gravitational field, their speeds, directions of motion, and the way these properties change from the outskirts of the bulge to its core, all carry information about how mass is distributed. In the Andromeda galaxy, this information points to a bulge, supported partly by random motions and partly by rotation, embedded in a larger halo of dark matter and wrapped around a central conic mass that deepens the potential well in the innermost region. The increasing speeds of stars toward the center are one of the clearest signatures of this deepening potential. In the context of a consistent model that respects the observed light, the most natural way to provide such a concentrated mass is through a supermassive black hole at the very heart of the bulge. The nuclear star cluster at the center of the Andromeda galaxy sits inside the already dense bulge and marks a further step inward toward the region where gravity becomes extreme. In images with modest resolution, the nucleus appears simply as a bright point of light at the center of the galaxy, but higher resolution observations reveal that this central region is not a single star, but a compact group of many stars packed into a small volume. The cluster extends over a span of only a few light years, which is tiny compared with the size of the bulge and disk. Yet within this region, the number of stars is very large. Their combined light creates a sharp peak in brightness that stands out even against the rising background of the bulge. To study this nuclear cluster, astronomers use telescopes with high angular resolution, including space-based observatories and ground-based instruments equipped with adaptive optics systems. These tools reduce blurring and allow the central light to be resolved into structure. With such data, it becomes possible to measure how the surface brightness of the cluster changes with distance from the exact center. The profile of this brightness, when compared with models of star clusters, shows that the central concentration is stronger than in many ordinary clusters found elsewhere in the galaxy, which points toward a particularly high central mass density. Within the nuclear star cluster, the stars are mostly old, but there is evidence for a mixed population that may include some younger stars as well. Spectroscopic observations of the light from this region reveal features that indicate a range of stellar types. By analyzing these spectra, astronomers infer that the nuclear cluster has experienced more than one episode of star formation over its history. Gas driven into the central region by dynamical processes in the bulge and disk can cool and form new stars from time to time, adding to the older population. This repeated building of the cluster over long periods increases its mass and tightens its connection to the central potential. The motions of stars inside the nuclear cluster carry direct information about the gravitational field at very small radii. However, individual stars in the Andromeda nucleus are not as easily tracked as those near the center of the Milky Way, because Andromeda lies farther away and the angular separation between stars is smaller. Instead of following single stars, astronomers often measure the average line of sight velocities of many stars blended together within small regions of the cluster. As in the bulge, they use the broadening and shapes of absorption lines in the integrated spectrum to derive the velocity dispersion in the cluster. In the outer part of the nuclear cluster, the dispersion has a high but roughly constant value, while closer to the center, it rises further. This pattern indicates that the gravitational potential deepens toward the exact center beyond what would be expected from the visible stars in the cluster alone. The structure of the nuclear cluster also shows that it's not simply an isolated ball of stars placed at the center of the galaxy. It is embedded in the broader gravitational field of the bulge and influenced by the global rotation of the inner disk. Some stars in the cluster follow orbits that are shaped by the overall angular momentum of the galaxy, while others move on more random paths, dominated by the local potential of the cluster and central mass. This combination of ordered and random motion creates a complex but stable configuration that can be explored with dynamical models. When astronomers construct such models, they include contributions from the bulge, the nuclear cluster, and an additional compact central mass. The contribution from the bulge is known from its light distribution on somewhat larger scales. The contribution from the nuclear cluster is constrained by the brightness profile within the inner few light years. The remaining degree of freedom is the presence or absence of a very compact, non-luminous mass at the exact center. Models that include only stars in the bulge and cluster tend to underestimate the observed velocity dispersion in the innermost part of the nucleus. When a central mass corresponding to a supermassive black hole is added, with a value inferred from broader dynamical studies of the galaxy, the predicted dispersions match the measurements significantly better. This outcome supports the idea that the nuclear cluster is wrapped around an unseen object that dominates the gravitational field within the smallest radii. In addition to velocity dispersion, astronomers look at subtle asymmetries in the brightness distribution of the nuclear cluster. High-resolution images show that the peak of light is not perfectly symmetric in all directions, and that the central structure is slightly elongated and offset on very small scales. These details suggest that stars in the cluster do not simply fill a smooth spherical region, but instead trace a more structured potential. Some of this structure can arise from stars moving on elongated orbits around a concentrated central mass, which leads to gentle variations in surface brightness that can be mapped and compared with dynamical models. The nuclear cluster, therefore, serves as a sensitive tracer of the central gravitational field. Even though the black hole itself cannot be seen directly, its mass affects how stars are distributed and how fast they move within this cluster. Over time, stars that pass very close to the unseen mass may have their orbits altered, leading to a slow reshaping of the cluster. The overall effect is that the innermost region is bound tightly to the central mass, while the outer parts of the cluster merge smoothly into the surrounding bulge. This nested structure, in which the disk and bulge feed gas inward, the gas forms stars in the nuclear cluster, and the cluster orbits around an even more compact mass, represents a natural continuation of the trend toward higher densities and stronger gravity as the center of the Andromeda galaxy is approached. In this setting, the nuclear star cluster is both a product of the galaxy's long-term evolution and a present-day probe of the conditions very close to the central black hole. Even though the black hole itself remains invisible in direct light, the apparent double nucleus of the Andromeda galaxy is one of the most striking features revealed when the central region is observed with very high resolution. Early images with modest sharpness show only a single bright peak of light at the galaxy's center, but when space-based telescopes and advanced ground-based systems observe the nucleus, they resolve two closely spaced peaks instead of one. These peaks sit within the same nuclear star cluster described earlier and are separated on the sky by a very small angle corresponding to a distance of only a fraction of a light year at the galaxy's location. For clarity, astronomers describe one of these peaks as the brighter photometric center and the other as a slightly fainter companion. Careful studies show that the brighter peak is not exactly at the dynamical center, the point around which stars in the nuclear region appear to orbit. This offset is an important clue because it suggests that the pattern of light does not directly trace the deepest part of the gravitational field. Instead, the brightest point in the nucleus marks a place where stars spend more time along their orbits, leading to an enhanced surface density of light, while the true center of mass, dominated by the unseen black hole and surrounding stars, lies nearby, but not exactly on this peak. In order to understand this structure, astronomers build models in which stars move on elongated orbits around a single central supermassive black hole. In such models, many stars share a preferred orientation of their orbits and have similar shapes, forming what is sometimes called an eccentric disk. Along these orbits, stars move more slowly near the farthest points from the center, and more quickly near the closest approaches, as expected in a gravitational field that weakens with distance. Because stars travel slowly near their outer turning points, they spend more time there, so the surface brightness appears higher in those regions when the light of many stars is added together. If a large group of stars follow such aligned elongated orbits around the black hole in the Andromeda nucleus, the place where these outer turning points cluster on the sky will look like an off-center brightness peak. The true gravitational center, which is close to the focus of the orbits where the black hole resides, can then be slightly displaced from the brightest part of the light distribution. This framework explains how a single central black hole and a surrounding population of stars can produce two light peaks without requiring two separate massive objects. Observational data support this picture in several ways. First, the overall velocity field of stars in the nuclear region is consistent with rotation and random motions around a single center rather than around two widely separated masses. Line-of-sight velocity maps show a pattern that crosses smoothly through the region between the two brightness peaks, with the point of maximum velocity gradient lying close to the inferred dynamical center rather than exactly on the brightest peak. This behavior matches expectations from an eccentric disk of stars orbiting one black hole. Second, the detailed shape of the brightness distribution along the line that connects the two peaks agrees well with predictions from models in which the nuclear stars occupy a disk of nearly Keplerian orbits, meaning orbits shaped primarily by the gravity of a central compact mass. These models reproduce the relative heights and widths of the two peaks and the way brightness falls off away from them. In particular, the brighter peak corresponds to the side of the disk where stellar orbits reach their outer points, while the fainter peak lies closer to the true center, where the stars pass quickly and do not linger to build up as much surface brightness. Third, when the integrated spectrum of the nucleus is analyzed in small spatial segments, the line of sight velocity dispersion and mean velocity change, with position in a way that favors a single centrally dominated potential. There is no dynamical signature of a second massive black hole of comparable mass on the scale separating the peaks. Instead, the mass distribution is consistent with one supermassive black hole whose sphere of influence extends over much of the nuclear cluster, surrounded by stars arranged in an eccentric configuration. The apparent double nucleus is therefore understood as a geometric and dynamical effect, rather than as evidence for two separate central black holes. This understanding matters for the broader goal of weighing the central black hole in the Andromeda galaxy. If the two peaks were separate massive objects, the interpretation of stellar motions and brightness patterns would be more complex and might imply a very different mass distribution. By adopting an orbital model in which a single black hole dominates and stars follow ordered yet elongated paths, astronomers can relate the observed kinematics and photometry to a single central mass more reliably. The match between such models and the data gives confidence that the Andromeda nucleus houses one supermassive black hole embedded in a nuclear star cluster whose structure reflects the long-term interaction between gravity, star formation, and orbital dynamics in the central region. In this picture, the apparent double nucleus becomes a natural, though initially surprising, outcome of stars moving in an ordered but eccentric disk around a single very massive central object. The development of this interpretation has relied on advances in both imaging and computation. Early high-resolution images first showed the unexpected double structure and prompted questions about whether Andromeda might host two nuclei. As spectroscopic and photometric data improved, and as numerical tools allowed more detailed dynamical models, the eccentric disk explanation became increasingly well tested. Modern observations continue to refine the properties of the nuclear cluster, including its total mass, the distribution of stellar orbits, and the exact position of the dynamical center relative to the light peaks. These refinements all point toward a stable configuration in which one dominant black hole shapes the central gravitational field, while the surrounding stars respond by settling into orbits that collectively produce the observed pattern of light. The double nucleus, once a puzzle, is now treated as a precise probe of both the mass and the spatial influence of the central black hole in the Andromeda galaxy. The measurement of stellar velocities in the very central region of the Andromeda galaxy turns the previous qualitative signs of strong gravity into a direct and quantitative estimate of the mass of the central black hole. At the distance of Andromeda, even the inner few light years of the galaxy project to a very small angle on the sky, so astronomers must use instruments that can both distinguish features on tiny angular scales and disperse the light into spectra with high precision. Space-based telescopes and large ground-based observatories with adaptive optics provide this capability, They can place narrow slits or small fields of view across the nucleus and record spectra that come from carefully chosen regions inside the nuclear star cluster. Each spectrum contains the combined light of many stars, whose motions along the line of sight cause subtle broadening and shifting of absorption. By comparing these observed line shapes with those of nearby template stars, whose properties are well known, astronomers extract the distribution of line-of-sight velocities at each position. This distribution is often described by a mean velocity, which traces ordered rotation, and a velocity dispersion, which reflects random motion. In the central parts of the Andromeda nucleus, both quantities carry important information. The mean velocity shows how fast stars as a group circle the center, while the dispersion reveals how strongly they are bound by gravity. Together, they define a velocity field that can be mapped across the nuclear region. Once this velocity field is measured, the next step is to interpret it in terms of an underlying mass distribution. For this purpose, dynamical models are built that connect the density of stars, their orbital structure, and the gravitational potential. One family of models assumes that the orbits are distributed in a relatively simple way and uses the equations of stellar dynamics to predict the expected rotation and dispersion for a given combination of bulge, nuclear cluster, and central compact mass. Another family allows a more flexible superposition of many possible orbits, each with its own weight, and searches for the mixture that best reproduces the observed velocities and surface brightness. In both cases, the mass of the central black hole enters as a parameter that can be adjusted. For each trial value of this mass, the model computes the predicted velocity field and compares it with the measurements. If the assumed black hole mass is too small, the model underestimates the steep rise in dispersion toward the center and cannot match the high speeds implied by the broadened lines in the innermost aperture. If the assumed mass is too large, the model predicts velocities that are higher than observed and a sharper central peak in dispersion than is present in the data. There is typically a narrow range of black hole masses for which the predicted velocities agree well with the measurements across the entire nuclear region. This range defines the best estimate of the central mass, and it's uncertain. In the case of the Andromeda galaxy, such modeling points to a black hole whose mass is equivalent to several tens or a few hundreds of millions of suns. This value is large enough that within a radius of only a few light years, the gravitational pull of the black hole dominates over that of the surrounding stars. Outside the sphere of influence, the combined mass of the nuclear cluster and bulge becomes more important, but the presence of the central black hole still leaves a clear imprint on the velocity field near the core. The precision of this mass estimate depends on several factors. One is the quality of the data, including the spatial resolution, the spectral resolution, and the signal-to-noise ratio of the spectra. Another is the accuracy with which the light distribution of the nuclear cluster and bulge is known, because this controls how well the stellar mass contribution can be separated from that of the black hole. A third factor is the set of assumptions made about the orbital structure of the stars. If orbits are allowed to vary in shape, inclination, and degree of anisotropy, the model can fit a wider range of velocity fields, but this flexibility also introduces degeneracies between the inferred stellar mass distribution and the black hole mass. To address these issues, astronomers often explore many model variants and examine how the inferred black hole mass changes when key assumptions are altered within reasonable limits. Despite these complexities, the central result remains robust. A model that includes a supermassive black hole provides a far better fit to the observed velocity field than any model that relies only on stars in the bulge and nuclear cluster. The difference is not limited to the overall level of dispersion, but also appears in the way velocities change with radius and position angle across the nucleus. Models without a black hole struggle to reproduce the combination of high central dispersion and the detailed pattern of rotation, whereas models with a black hole can match both features simultaneously. The success of such models reinforces the view that the nuclear star cluster is orbiting around a single dominant compact mass. These dynamical measurements of stellar velocities therefore serve as a direct weighing of the Andromeda black hole. Unlike indirect arguments based on scaling relations or global properties of the galaxy, the mass estimate derived from the nuclear kinematics rests on the gravitational influence that the black hole exerts on stars only a few light years away. By measuring how fast those stars move and how their speeds change as one approaches the center, the astronomers read the depth of the central potential and convert it into a mass in a way that depends only on well-established laws of gravity. In this sense, the nuclear velocity field is not just a map of motions, but a measurement tool that transforms the light of many unresolved stars into a precise estimate of the mass of the supermassive black hole at the core of the Andromeda galaxy. Gas in the central region of the Andromeda galaxy offers an independent way to probe the mass of the central black hole because this gas responds directly to gravity and can produce clear spectral features that record its motion. While stars in the nuclear cluster move on many different orbits, and their combined light must be interpreted statistically, gas often settles into disks or rings where its motion is more ordered. In the inner part of Andromeda, observations reveal ionized gas and warmer components that emit light at specific wavelengths, forming bright emission lines in the spectrum. By measuring how these lines shift and broaden at different positions across the nucleus, astronomers can map the motions of the gas and compare them with the gravitational field inferred from the star. This mapping is an exercise in gas kinematics, meaning the study of how gas moves under the influence of gravity and other forces. High-resolution spectroscopy shows that close to the center of Andromeda, ionized gas forms a rotating structure whose velocity pattern changes rapidly with radius. Along a line that passes through the nucleus, the emission lines shift to shorter wavelengths on one side and to longer wavelengths on the other, indicating that gas on one side moves toward the observer, while gas on the opposite side moves away. The size of these shifts corresponds to speeds that rise as the measured position approaches the nucleus. At the same time, the lines are broadened in a way that signals a mix of ordered rotation and internal motions, such as turbulence or small-scale random flow. When these data are assembled into a two-dimensional velocity field, they show a clear organized pattern of rotation around a central point within a very small region. To interpret this pattern, astronomers construct models in which gas moves along nearly circular or slightly elliptical paths in a thin disk around a central mass. In the simplest version, the gas is assumed to follow orbits determined mainly by gravity, with pressure forces and other effects treated as smaller corrections. The gravitational potential in such models has contributions from the stars in the bulge and nuclear cluster and from the central black hole. For each assumed distribution of mass, the model predicts how fast gas should move at each radius and how the velocity field should look when projected on the sky. These predicted velocities can then be transformed into line-of-sight components and compared directly with the observed emission line shifts. If a model lacks a central black hole, the enclosed mass within the innermost radii is limited to the stars present there. In that case, the predicted gas rotation speeds near the center are lower than observed because the stellar mass alone does not create a strong enough gravitational field to hold gas in such rapid orbit. The discrepancy is most apparent within the inner fractions of a light year, where observed velocities change steeply with radius and reach high values over a short distance. When a compact central mass consistent with the supermassive black hole inferred from stellar dynamics is added to the model, the predicted gas velocities increase in the inner region, and the shape of the rotation curve becomes much closer to what the data show. In many studies, only models that include a black hole succeed in matching both the maximum speeds and the way velocities fall off away from the center. The widths of the emission lines add further constraints. Gas in a thin, well-ordered disk would produce lines broadened mainly by the range of velocities along the line of sight within each resolution element. If random motions, turbulence, or inflows and outflows contribute strongly, the lines would also show additional broadening that is not tied directly to rotation. By examining the line profiles carefully, astronomers can estimate how much of the broadening arises from ordered rotation and how much from internal motions. In the Andromeda nucleus, the line profiles indicate that rotation is the dominant contributor to the observed width near the center, which strengthens the link between the measured velocities and the underlying gravitational field. Models that incorporate both a rotating disk and a central black hole reproduce the observed line widths more faithfully than models without a black hole, again pointing to a heavy compact mass in the core. In addition to ionized gas, there is evidence for molecular gas in the inner region. This colder component can be traced by radio observations of specific molecular transitions. The molecular gas tends to form rings or clumps at somewhat larger radii than the innermost ionized gas, but its motion still feels the combined pull of the bulge, nuclear cluster, and black hole. The pattern of velocities in these molecular structures often aligns with the rotation of the inner disk, extending the kinematic picture over a broader range of radii. By matching both the ionized and molecular gas motions with a single mass model, astronomers check the consistency of their interpretation. A model that works for one gas component and fails for the other would be less convincing than one that explains both. In practice, the presence of a supermassive black hole with a mass similar to that derived from stellar velocities allows a unified description of the gas dynamics across the inner region. There are, however, uncertainties and complications in using gas as a tracer. Gas can be pushed by radiation, magnetic fields, and pressure gradients, and it can move in non-circular flows, such as spirals or inflows toward the center. Shocks can form where gas streams intersect, and heating or cooling can change the local sound speed and turbulence level. To avoid misinterpreting such effects as pure gravity, astronomers focus on regions where the velocity field appears smooth and symmetric, and where there is little sign of strong disturbances. In Andromeda, although the gas structure near the nucleus is not perfectly regular, there are parts of the inner disk where the rotation pattern is so orderly that gravitational models remain reliable. By limiting the analysis to these zones and allowing for moderate non-circular motions in the modeling, researchers can still extract a robust estimate of the central mass. When the best-fitting gas dynamical models are compared with stellar dynamical results, they converge on a similar mass for the central black hole within the uncertainties. Gas and stars have very different responses to forces beyond gravity. Stars move mainly under gravity and preserve their orbits over long times, while gas is more easily redistributed by other processes. The fact that both tracers point to the same central mass strengthens the conclusion that the Andromeda nucleus contains a supermassive black hole with a well-defined gravitational sphere of influence. Gas motions in this sense act as a cross-check on the stellar evidence. Together, they show that the central mass required to explain the rapid rotation and high dispersions in the inner region cannot be supplied by ordinary stars alone, and is most naturally provided by a single compact black hole at the core of the Andromeda Galaxy. The central black hole in the Andromeda Galaxy reveals itself most clearly when astronomers look at the nucleus across many different wavelengths of light. Each part of the spectrum responds to different physical conditions, so a combined view helps describe both the location and the present activity level of the black hole. In visible light, the nucleus is dominated by the stars of the nuclear cluster and the inner bulge. The black hole does not emit visible light directly, and any hot gas close to it is too faint to stand out against the strong stellar background. To reduce this glare, observers turn to other bands where the contrast between stellar light and non-stellar processes becomes more favorable. In the infrared, the nuclear region can be seen through much of the dust that lies along the line of sight. Infrared observations show the shape of the nuclear star cluster and the double peak structure described earlier, but they also help to isolate any compact emission that does not follow the stellar distribution. Warm dust and gas heated by weak accretion or by the general radiation field of the nucleus emit in these wavelengths. By subtracting models of the stellar light, astronomers can search for small residuals that might trace material linked more directly to the central black hole. These residuals are modest in Andromeda, consistent with a low level of current activity, rather than a bright active nucleus. In the radio band, very compact sources are often associated with jets or outflows from accreting black holes. In the case of the Andromeda nucleus, radio observations reveal a faint central radio core located very close to the dynamical center, derived from stellar motions. The radio emission is weak compared with that of powerful active galactic nuclei, yet it is distinct from the broader radio emission of star-forming regions elsewhere in the galaxy. The compactness of this radio core, together with its position at the center of the potential well, supports its identification with the immediate environment of the supermassive black hole. The spectrum of this radio source, which describes how its brightness changes with frequency, is consistent with emission from a small region of relativistic particles and magnetic fields near the black hole, rather than from a large population of normal stars. Moving to higher energies, X-ray observations supply another key piece of information. Hot gas at temperatures of millions of degrees emits X-rays, and such gas can arise near a black hole where matter falls inward and is heated by compression and friction. In the Andromeda nucleus, X-ray telescopes detect a compact source close to the same central position, marked by the radio core. The luminosity of this source is low when compared with that of bright quasars or strong Seyfert-type nuclei, but it is measurable and provides a direct sign that some gas is currently being heated in the vicinity of the black hole. At the same time, the nuclear region contains other X-ray sources associated with X-ray binaries and supernova remnants. So careful analysis is needed to separate the emission of the central black hole from that of nearby compact systems. High-resolution X-ray imaging helps by resolving individual sources and tracking their variability. The central source associated with the black hole tends to vary more slowly and remains at a persistently low luminosity, whereas binary systems often show stronger and more rapid changes. By monitoring these patterns over time, astronomers isolate the contribution of the black hole to the total X-ray output. When the radio, infrared, and X-ray data are combined, They form a spectral energy distribution of the nucleus that can be compared with theoretical models of accretion flows around black holes. In the Andromeda galaxy, this distribution is characteristic of a system with a very low accretion rate. The black hole has a large mass on the order of many tens or perhaps a few hundreds of millions of solar masses, but it currently receives matter only at a small fraction of the rate that would produce a luminous active nucleus. Under such conditions, accretion is thought to proceed in a way that converts only a modest share of the gravitational energy of infalling gas into radiation. Much of the energy may instead remain in the gas as heat or be carried away by outflows that are not very bright. These models, often described as radiatively inefficient accretion flows, match the low radio and X-ray luminosities of the Andromeda nucleus, while still allowing for a significant amount of gas to be present close to the black hole. The multi-wavelength view also allows a comparison with the central black hole and the Milky Way, which is similarly underluminous relative to its mass. Both systems show faint radio cores and weak X-ray emission, and both lack the strong, broad emission lines and powerful jets seen in more active nuclei. The Andromeda nucleus, however, appears in some studies to be even dimmer than the Milky Way center when scaled by black hole mass, suggesting that its current accretion rate may be smaller still, or that its accretion flow has a different structure. These comparisons underline the diversity of black hole feeding states, even among nearby galaxies with similar overall properties. Ultraviolet observations add further constraints by probing the presence of hot stars and potential non-stellar continuum in the nucleus. In Andromeda, the ultraviolet light is dominated by a population of stars in and around the nuclear cluster, with only a small or uncertain contribution from any accretion-related emission. This reinforces the view that at present, the black hole plays a minor role in the overall light output of the nucleus, even though it dominates the gravitational field within the inner few light years. The nucleus is, in this sense, dynamically centered on the black hole, but radiatively dominated by stars. Observers also search for signs of outflows driven by the central engine, such as faint radio jets or disturbed gas features in optical and infrared lines. In Andromeda, any such signatures are extremely weak or absent on the scales that can be resolved, again consistent with a very low level of nuclear activity. Gas motions near the center appear to be governed mainly by gravity and by the general dynamics of the bulge and nuclear cluster rather than by strong winds or jet. The multi-wavelength data do, however, reveal a complex environment in which small changes in the supply of gas to the inner region could lead to variations in the luminosity of the central source over long time. Altogether, the multi-wavelength view of the Andromeda nucleus presents a picture of a massive black hole in a quiet state. Radio, infrared, ultraviolet, and X-ray observations converge on a consistent central position and show that some accretion and heating are taking place, but at a level far below that seen in classical active galactic nuclei. The black hole is firmly present in the dynamics, as earlier sections describe, yet it contributes only a small fraction of the total light from the central region at the current epoch. This combination of strong gravitational influence and low radiative output makes the Andromeda nucleus an important example for understanding how supermassive black holes can spend long periods in weakly active states, while still shaping the motion of stars and gas in their immediate surroundings. The central black hole in the Andromeda galaxy can be placed in a wider context by comparing its mass and current activity with those of other known supermassive black holes. Dynamical models that match the motions of stars and gas in the nucleus point to a mass of many tens or perhaps a few hundreds of millions of times the mass of the Sun. This value is not exact because it depends on details of the models and on how the stellar mass in the bulge and nuclear cluster is estimated, but it falls securely in the range of what astronomers call supermassive black holes. When this mass is compared with that of the central black hole in the Milky Way, an interesting contrast appears. The black hole at the center of the Milky Way, associated with the radio source known as Sagittarius A, has a mass of only a few million solar masses as measured very precisely from the orbits of individual stars. The Andromeda black hole is therefore much heavier by about an order of magnitude or more, yet both galaxies have roughly similar overall sizes and belong to the same small group. This difference suggests that the details of each galaxy's formation and growth history have allowed their central black holes to evolve along somewhat different paths. Even though the mass of the Andromeda black hole is large, it is still modest compared with the most extreme examples known in the universe. In giant elliptical galaxies at the centers of large clusters and in luminous quasars, black holes can reach masses of billions of solar masses. These extreme objects power bright active galactic nuclei whose light can outshine all the stars in their host galaxies. By contrast, the Andromeda nucleus is faint. Its black hole mass lies in the lower part of the range for massive galaxies, and its output at radio, infrared, and X-ray wavelengths is low compared with the energy that would be released if matter were falling in at a high rate. When astronomers compare the brightness of Andromeda's nucleus with the maximum steady brightness that a black hole of that mass could in principle sustain before radiation pressure begins to push much of the infalling gas away, they find that the present output is many orders of magnitude below this limit. In other words, the Andromeda black hole is not short of capacity to radiate. It is short of fuel, or the fuel that does reach it emits only a small fraction of its available gravitational energy as light. The Milky Way black hole shows a similar pattern on a smaller mass scale. It is underluminous compared with its potential, and its radio and X-ray emission are weak and variable. In some respects, the Andromeda nucleus is even dimmer when scaled to its black hole mass, which suggests either an even lower present-day inflow of gas or a different internal structure of the accretion flow that reduces its radiative efficiency. Both black holes are therefore examples of supermassive objects that currently live in a quiet state with limited accretion and modest radiation, embedded in galaxies where most of the visible light comes from stars rather than from the central engine. Comparing these two nearby systems has helped to build a broader picture in which supermassive black holes do not shine steadily at high levels throughout cosmic time. Instead, they alternate between active phases when abundant gas reaches the central regions, and long intervals when the gas supply is sparse or hot and the nucleus is faint. The Andromeda black hole appears to be in such a low state now. Its mass is large enough that even a small change in the inflow of gas would raise its luminosity substantially, but current observations show no sign of strong activity. When the Andromeda black hole is compared with more distant, brighter active galactic nuclei, its mass sits in a range where many active systems have been found, but its luminosity is closer to that of dormant or weakly active nuclei in nearby galaxies. This comparison highlights that mass alone does not determine how bright a black hole appears. The rate at which matter is supplied, the physical state of the gas, and the geometry of the inflow all play a role. In the Andromeda nucleus, the gas seems to be present mainly in low density and perhaps in forms that do not cool efficiently as they fall inward, which reduces the fraction of gravitational energy that emerges as radiation. Another way to place the Andromeda black hole in context is to examine empirical relations that link black hole mass to the properties of the host galaxy, especially to the mass or velocity dispersion of the bulge stars. In many galaxies where black hole masses have been measured, there is a correlation between the mass of the central black hole and the characteristic random speed of stars in the bulge. This relation suggests some kind of long-term connection between the growth of the bulge and the growth of the black hole. When the Andromeda galaxy is plotted on this relation using its bulge velocity dispersion and the black hole mass derived from dynamical models, it falls within the general scatter of other galaxies, perhaps slightly above the mean line in some studies, but not as an extreme outlier. This placement indicates that despite its low present activity, the Andromeda black hole is typical of black holes found in galaxies with similar bulge properties. It has grown to a mass that fits with the general trend linking central black holes and stellar bulges, implying that over long times, its growth has been broadly in step with that of its host galaxy. Comparisons can also be made with other nearby spiral galaxies that host measured black holes. Some of these galaxies have central masses closer to that of Sagittarius A, while others have masses similar to or larger than that in Andromeda. Their nuclei span a wide range of activity levels, from bright Seyfert-type systems to very faint cores. The Andromeda nucleus sits toward the faint end of this distribution. It is not unique in this respect, but rather part of a population of low luminosity nuclei, whose black holes are known mainly through their gravitational effects on stars and gas, rather than through their radiation. This population is important because it suggests that in the present epoch, many massive nearby galaxies are in a state of weak or intermittent accretion. In terms of energy balance within the host galaxy, the Andromeda black hole now contributes relatively little direct radiation or mechanical power compared with star formation and other processes. However, its mass is high enough that any sustained increase in accretion rate over cosmic time could have injected significant energy into the surrounding gas, perhaps helping to regulate the growth of the central regions in the past. Observations of distant galaxies, which show many more bright active nuclei at earlier epochs, support the idea that black hole activity rates have declined over time. The Andromeda black hole can then be viewed as a massive remnant of a growth phase that was more vigorous in the past, even though its present state is calm. When mass, activity, and host galaxy properties are all considered together, the Andromeda black hole emerges as a representative example of a supermassive black hole in a large spiral galaxy in the local universe. Its mass falls within the range expected from the bulge properties. Its current luminosity is low, but consistent with a weak accretion flow, and its influence on stellar and gas motions near the center is strong enough to be measured in detail. These points of comparison, taken as a whole, show that the Andromeda black hole is neither an extreme giant nor a minimal case, but a significant central mass whose present quiet state fits into the broader pattern of supermassive black holes and their host galaxies in the nearby universe. The present state of the central black hole in the Andromeda galaxy is shaped not only by its mass, but also by the way gas flows onto it. This flow, called accretion, is the process by which matter gradually loses energy and spirals inward under the pull of gravity. In bright active galactic nuclei, accretion can form a dense cool disk that radiates strongly at many wavelengths. In the Andromeda nucleus, the situation appears different. The observed radio and X-ray luminosities are low, even though the black hole mass is large, which points toward a flow that is both weak in total rate and inefficient at turning gravitational energy into light. To describe this structure, Astronomers combine clues from observations with theoretical models of gas in strong gravity. Gas that reaches the inner regions around the black hole likely comes from several sources. Some of it may drift inward from larger radii in the form of diffuse interstellar gas in the bowl. Some may be supplied by stellar winds from stars in the nuclear cluster, which shed material into the surrounding space. Occasional disrupted clouds or small infalling structures may contribute as well. However, by the time gas approaches the sphere of influence of the black hole, its overall density appears to be low. X-ray observations show only moderate amounts of hot gas, and there is no sign of the very bright optical or ultraviolet emission lines that would accompany dense, rapidly cooling material. This suggests that the accretion flow in Andromeda is hot and rarefied, with particles that move quickly and interact in ways that keep much of the gravitational energy as internal heat, rather than radiating it away. In such a flow, gas does not fall straight inward. It carries angular momentum, which means it has some net rotation around the center. As a result, the gas settles into a rotating structure that may resemble a thick, puffed-up disk or torus rather than a thin, cold disk. Friction and magnetic processes inside this rotating gas cause material to move slowly inward, while some angular momentum is transported outward. The inward drift is gradual, and the time it takes for gas to reach the black hole can be long compared with the orbital period because the density is low and the particles are hot. Collisions are relatively infrequent, so the gas can stay at high temperature as it moves inward. Under these conditions, radiation escapes less efficiently than in a dense, cool disk, and a significant fraction of the energy carried by the gas can be dragged inward across the innermost region without being emitted as light. This type of structure is what astronomers refer to when they speak of a radiatively inefficient accretion flow. The low radiative efficiency is reflected directly in the faintness of the nucleus. For a given mass of the black hole, theories predict how bright the nucleus would be if gas were being supplied at some fraction of the rate that would lead to strong radiation pressure. In Andromeda, the observed luminosity implies either that the actual inflow rate is extremely small compared with these standard rates, or that the flow has properties that reduce its ability to emit. Both effects may be present. The observed radio emission suggests that some energetic particles and magnetic fields are present near the black hole, consistent with a hot magnetized flow. The weak but persistent X-ray source indicates that a portion of the gas is heated to very high temperatures and does radiate, though not at the level seen in more active systems. The detailed structure of the flow remains difficult to image directly because the angular size of the region close to the black hole is too small to resolve with current telescopes at the distance of the Andromeda galaxy. Instead, astronomers rely on indirect constraints. The spectral energy distribution of the nucleus, assembled from radio to X-ray wavelengths, lacks the strong bump in ultraviolet and optical light that marks a classic thin accretion disk. Instead, it rises modestly toward higher energies and shows a relatively strong radio component compared with the total luminosity. Models that reproduce this spectrum often include a hot, thick inner flow that produces the X-rays and part of the radio emission, plus possible contributions from a very weak outer disk or from jets that carry energy away mechanically. In the Andromeda nucleus, any jet appears to be faint and not clearly resolved, so most of the emphasis falls on the inner flow itself. The geometry of this flow in Andromeda is not fully known. It may be approximately aligned with the larger scale rotation of the nuclear star cluster or the inner gas disk. or it may be tilted by past events. Small tilts can cause warps and twists in the flow, which might influence how gas is fed inward from different directions. On larger scales, molecular gas in rings and patches shows that cold material does exist at some distances from the center, but this cold gas does not appear to be streaming rapidly into the nucleus at the present time. Instead, it likely feeds the inner hot flow slowly through a combination of gravitational torques and internal instabilities that act over long periods. In some models, a significant fraction of the gas that reaches the inner regions may not cross the event horizon at all, but instead be driven outward in winds. These winds carry mass, energy, and angular momentum away from the black hole and can reduce the net accretion rate. Observationally, such winds would appear as broad, weak features, or as subtle shifts in emission lines that trace gas moving outward from the nucleus. In the Andromeda galaxy, clear signatures of strong nuclear winds have not been firmly detected on the scales that are resolved, but mild outflows cannot be ruled out. If they exist, they would help explain how the accretion flow remains hot and dilute by removing some of the gas before it can cool and settle into a denser configuration. The stability of the low accretion state in Andromeda is also a subject of study. If gas supply from the bulge and nuclear cluster changes over time, the accretion rate and the associated luminosity could vary. Long-term monitoring shows that the nuclear X-ray source fluctuates, though within a range that remains low overall. These variations suggest that the inner flow is dynamic, responding to changes in gas input and to internal processes such as magnetic reconnection and turbulent mixing. However, there is no sign of large sudden transitions into a bright state in recent observations. This steadiness supports the view that the inner flow is settled into a long-lived configuration in which the black hole is lightly fed by hot, low-density gas. The structure of the low accretion flow, therefore, provides a bridge between the purely dynamical evidence for the black hole based on stellar and gas motions and the faint radiation that emerges from its immediate surroundings. By combining theoretical models of hot rotating gas with multi-wavelength observations, astronomers build a coherent picture in which the Andromeda black hole is surrounded by a radiatively inefficient flow whose density and temperature are set by the modest supply of gas from the surrounding bulge and nuclear cluster. This flow generates the weak radio and X-ray emission that mark the presence of the black hole, while allowing most of the gravitational energy of the infalling gas to remain locked in the motion and heat of the flow, rather than being converted into bright radiation. In this way, the structure of the low accretion flow helps explain how a very massive black hole can remain nearly invisible in terms of light, while still playing a central role in shaping the motions and conditions in the heart of the Andromeda Galaxy. Close to the central black hole in the Andromeda Galaxy, gravity enters a regime where ordinary Newtonian descriptions are no longer sufficient, and general relativity is needed to describe how matter and light. On larger scales throughout the bulge and nuclear star cluster, the motions of stars and gas can be understood quite well by treating gravity as a force that acts between masses and causes orbits that resemble slightly distorted ellipses. As the radius shrinks to only a few times the characteristic scale set by the black hole mass, this picture breaks down. In this inner domain, the black hole does not simply pull on its surroundings, it shapes the geometry of space and time themselves. General relativity describes gravity not as a force in the usual sense, but as curvature of spacetime caused by mass and energy. A supermassive black hole, such as the one in the Andromeda nucleus, creates very strong curvature in its immediate neighborhood. Free-falling matter and light follow paths that are determined by this curved geometry. These paths, called geodesics in the theory, differ from the simple conic sections that arise in Newtonian gravity. Orbits no longer close neatly on themselves, but slowly rotate, and the behavior of light is affected in ways that have no counterpart in a purely Newtonian framework. For a black hole with a mass of many tens or a few hundreds of millions of solar masses, the region where these relativistic effects are strong extends over a radius comparable to the inner part of a planetary system. Within several times this radius, orbital speeds reach a significant fraction of the speed of light, and the shapes of trajectories become highly sensitive to the exact geometry of the spacetime. If the black hole has little or no spin, the geometry is described by a simple spherically symmetric solution of the field equations. If the black hole rotates, the geometry becomes more complex and includes effects such as frame dragging, in which the rotation of the black hole causes nearby spacetime to be slowly carried around with it. In both cases, the curvature increases steadily as one moves inward and becomes extreme in the deepest part of the potential well. In the relativistic region around the Andromeda black hole, test particles on bound orbits experience precession of their closest approach point. Instead of following fixed ellipses, their orbits slowly swivel in space. This effect arises because the spacetime curvature near the black hole changes the relation between radius, speed, and orbital period. Compared with the Newtonian case, the precession is small for orbits that remain at large radii, but grows rapidly for orbits that dip close to the black hole. Stars in the nuclear cluster mostly move outside the zone where this effect becomes dominant, so their orbits can be approximated with less complex model. Gas in the inner accretion flow, however, can reach radii where relativistic corrections are essential. There, the paths of the gas and any associated magnetic fields are shaped by the full general relativistic structure of the gravitational field. Light that passes near the Andromeda black hole also feels the curvature of spacetime. Instead of traveling in straight lines through a fixed background, light rays bend when they pass close to the center. This bending is strongest for rays that skim the inner region and weaker for those that stay farther away. The result is a form of gravitational lensing in which the black hole and the matter around it slightly distort the apparent positions and shapes of background sources. In the case of the Andromeda galaxy, this lensing near the central black hole is extremely subtle because the region of strong bending covers a very small angle on the sky at its distance. Current telescopes cannot resolve these fine details, but the same physical principles that explain more easily observed lensing on larger scales apply here as well. The curvature also affects the energy of light that climbs out from the deep potential well. Photons emitted by hot gas near the black hole lose energy as they escape, a process known as gravitational redshift. To a distant observer, this loss appears as a shift of the light toward longer wavelengths. If gas in the inner accretion flow emits X-rays or other high-energy radiation, the spectrum of this radiation carries the imprint of both the orbital motions of the gas and the gravitational redshift. In very bright active galactic nuclei, these combined shifts and broadenings of spectral lines provide direct evidence of relativistic effects. In the Andromeda nucleus, the emission is too faint for detailed line profiles of this kind to be measured with current instruments, but models of the accretion flow still include gravitational redshift as an essential ingredient in describing any radiation that emerges from the innermost region. Time itself behaves differently near the central black hole compared with regions farther out. In general relativity, the rate at which time passes depends on the gravitational potential. Clocks placed deeper in a potential well tick more slowly as seen from a distant vantage than clocks placed farther away. In the context of the Andromeda black hole, this means that processes occurring very close to the black hole unfold in terms of proper time measured locally at a normal pace, but signals from those processes when viewed from Earth appear slightly slowed and redshifted because they must climb out through curved spacetime. For a supermassive black hole, this gravitational time dilation becomes significant only very close to the center, within a range of radii comparable to those that shape the inner accretion flow. The same relativistic region influences the stability of circular orbits. In Newtonian gravity, circular orbits can exist at essentially any radius around a point mass, provided the orbital speed is adjusted appropriately. In the relativistic field of a black hole, there is a minimum radius inside which no stable circular orbit is possible. Orbits there either plunge inward or are strongly distorted. The exact location of this transition depends on the mass and spin of the black hole. For the Andromeda black hole, this critical radius lies only a few times beyond the characteristic radius that sets the scale of the event horizon. Outside this region, circular orbits can exist and form part of the structure of the accretion flow. Inside it, matter that tries to maintain a circular path becomes dynamically unstable and drifts inward rapidly. Although this inner boundary of stability cannot be directly imaged in Andromeda, it plays a central role in theoretical descriptions of how gas behaves near the black hole and of how energy is released as matter makes its final orbits before crossing into regions from which no signals return. The relativistic character of the central gravitational field also affects how energy and angular momentum are transported in the flow. Magnetic fields that thread the hot gas can tap into the rotational energy of the black hole if it spins, a process that changes the structure of the space-time in subtle ways and may launch weak outflows even in low luminosity systems. In the Andromeda nucleus, any such extraction of rotational energy is likely modest given the low overall accretion rate, but it is part of the general framework used to understand black hole environments. The presence of a relativistic region means that gas does not simply fall inward under a calical force law, but interacts with a curved space-time that can in principle store and release energy in forms that would not exist without general relativity. In summary, the innermost domain around the Andromeda's black hole is a region where space and time are strongly curved, where orbits of matter deviate from simple Newtonian forms, and where the paths and energies of light are altered by gravity. Even though current observations cannot resolve this region directly in the Andromeda galaxy, the same relativistic principles that have been tested in other contexts and in other systems are applied to describe it. The dynamical evidence for a massive compact object at the center, combined with the multi-wavelength signatures of weak accretion, points toward a central environment dominated by a relativistic gravitational field, whose properties follow from the mass of the black hole and the laws of general relativity. At the very center of the Andromeda galaxy, the mass of the central black hole defines two especially important scales in its relativistic environment: the event horizon and the radius of the last stable circular orbits. The event horizon is the outer boundary of the region from which no signal can escape to the rest of the universe. It is not a physical surface in the usual sense, but a one-way threshold in spacetime. Inside this boundary, all possible paths in spacetime lead inward, and not even light, which travels at the highest possible speed, can move outward and reach distant observers. Outside the event horizon, matter and light can in principle follow paths that either remain in orbit or eventually move away. The position of the event horizon depends only on the mass of the black hole and if the black hole spins on its rotation. For a non-rotating black hole, general relativity gives a radius of the event horizon that scales directly with the black hole mass. A black hole with a mass of several tens or a few hundreds of millions of times the mass of the Sun has an event horizon whose size is measured in units comparable to the inner part of a planetary system. The distance of the Andromeda galaxy, such a region subtends an angle far too small to resolve with current telescopes, so the event horizon cannot be seen directly. Its presence is inferred from the fact that the central mass must be confined within a volume no larger than this scale in order to match the observed stellar and gas motions, and from the understanding that any smaller configuration of ordinary matter would be unstable over long times. If the Andromeda black hole spins, as many astrophysical black holes are expected to do, the shape and size of the event horizon change slightly. The horizon remains a closed surface, but it becomes smaller along the axis of rotation than in the equatorial plane. In addition, the rotating space-time around the black hole includes a region outside the event horizon where space itself is dragged in the direction of the spin, a phenomenon known as frame dragging. Although these details affect the precise geometry, the main point remains that there is a clear boundary inside which outward motion is impossible. The material in the accretion flow and any radiation it produces must cross this boundary if it comes too close, and after that crossing, no further direct information can reach observers outside. Just outside the event horizon lies another key radius, that of the last stable circular orbit. This is the smallest radius at which matter can move on a circular path around the black hole without rapidly spiraling inward. In Newtonian gravity, circular orbits can exist at any radius with the correct speed. In general relativity, the curvature of spacetime near a black hole changes this situation. There is a critical radius inside which circular orbits become unstable. Small disturbances then cause an orbiting particle or gas element to plunge inward rather than return to a slightly shifted circle. The exact location of this last stable orbit depends on the spin of the black hole and on whether the orbit moves in the same direction as the spin or in the opposite direction. For a non-rotating black hole, the last stable circular orbit lies at a radius several times larger than the radius of the event horizon. If the black hole spins and matter orbits in the same sense as the rotation, this stable radius moves inward, closer to the horizon. If matter orbits against the spin, the stable radius moves outward. In all cases, the region between the last stable orbit and the event horizon is one where circular motion cannot persist for long. Matter that crosses the last stable radius begins a rapid inward spiral, completing only a small number of orbits before it passes through the horizon. In the context of the Andromeda black hole, these radii set the inner edge of any long-lived disk-like structure in the accretion flow. Gas that drifts inward from larger distances can settle into nearly circular orbits down to the last stable radius. There it reaches a point where orbital support against gravity can no longer hold for small perturbation. The gas then plunges inward in what is sometimes called the inner plunging region, crossing the event horizon after losing the remaining angular momentum and energy needed to fall freely. During this final stage, a portion of the gravitational energy is converted into heat, and in radiatively efficient flows into radiation. In the low luminosity nucleus of Andromeda, the flow is believed to be radiatively inefficient, so a smaller fraction of this energy emerges as light. But the same basic structure of an inner stable region and an unstable plunging region apply. These relativistic radii also influence how much gravitational energy can be extracted from infalling matter before it disappears inside the horizon. The closer stable orbits can approach the horizon, the more energy can in principle be released. For a non-rotating black hole, matter that falls in from very large distances and passes through the last stable orbit before plunging inward can convert a certain fixed fraction of its rest mass energy into radiation if the flow is efficient. For a rapidly rotating black hole with orbits that co-rotate with the spin, this fraction can be higher because the last stable orbit lies close to the horizon and the gravitational field is stronger there. In both cases, the actual efficiency in a given system depends not only on these theoretical limits, but also on the detailed structure of the accretion flow. In the Andromeda nucleus, the presence of a radiatively effectively flow means that much of the available energy remains in the gas or is carried away in mechanical form, rather than emerging as light. Observationally, the event horizon and last stable orbits manifest themselves indirectly through the spectral and timing properties of emission from the innermost. In bright, active galactic nuclei, broadened and skewed spectral lines, especially from heavy elements such as iron, show that radiation is coming from regions where orbital speeds and gravitational redshifts are strong, often down to close to the last stable orbit. Rapid variability on timescales comparable to the orbital period at these radii also points to processes occurring near this inner edge. In the Andromeda galaxy, the nuclear emission is too faint to allow such detailed spectral studies at present, and rapid variability is difficult to measure with the necessary precision. Nevertheless, theoretical models of the low accretion flow assume that the same relativistic structure of spacetime governs the inner boundary conditions. The gas is expected to orbit down to the last stable radius and then plunge inward, with the event horizon providing the final limit beyond which information is lost to outside observers. The positions of the event horizon and last stable orbits, therefore, define the deepest part of the gravitational field of the Andromeda black hole. They mark the transition from orbits that can in principle be long-lived and observable to paths that lead inevitably inward. Although current instruments cannot resolve these scales in the Andromeda nucleus, the combination of dynamical mass measurements and general relativity specifies their radii once the mass and spin are known or estimated. In this way, the event horizon and last stable orbits form a conceptual inner frame around which descriptions of the accretion flow, the release of energy, and the motion of matter near the central black hole are built, even when the direct observational signatures of these boundaries remain out of reach. When stars and gas clouds move through the inner region of the Andromeda galaxy, their behavior changes as they enter the domain where the gravity of the central black hole dominates over that of the surrounding stars. Far from the center, a star in the nuclear cluster or bulge moves mainly under the combined pull of many stars and dark matter. Its path can take it closer to or farther from the nucleus over time, but remains largely set by the smooth gravitational potential of the bulge. As the orbit of such a star evolves through long-term interactions with other stars, and with the overall potential, there is a small chance that it will be scattered onto a trajectory that carries it deep into the sphere of influence of the black hole. In that inner region, the gravitational field changes rapidly with radius, and the outcome of a close passage depends sensitively on how near the star comes to the central mass. If the closest approach remains well outside a certain characteristic distance known as the tidal radius, the star stays intact. It feels a strong but nearly uniform gravitational pull across its volume and moves on a highly elongated orbit that swings sway in the center and returns to larger radii. In this case, the star acts as a test particle that samples the inner potential without suffering direct damage. Its orbit may precess and change shape over many passages due to further interactions, but the star itself remains bound and continues to participate in the dynamics of the nuclear region. If, however, the closest approach falls below the tidal radius, the difference in gravitational pull between the near and far sides of the star becomes large enough to overcome the star's own self-gravity. At that point, the star is tidally disrupted. In theoretical descriptions, the stellar material is stretched and compressed, and the star is pulled apart into a stream of gas that follows a highly elongated path around the black hole. Roughly half of this gas can, in many models, acquire enough energy to escape the system, while the other half remains gravitationally bound and eventually returns toward the black hole along its orbit. When this returning material interacts with itself and with any pre-existing gas, it can lose energy and settle into an accretion flow, leading to a temporary increase in the rate at which matter falls onto the black hole. In other galaxies, such tidal disruption events have been seen as bright, short-lived flares, especially at ultraviolet and X-ray wavelengths, that fade over time as the supply of bound debris is consumed. In the Andromeda galaxy, no very strong and clearly isolated tidal disruption flare from the center has yet been identified with high confidence in current data. Although the nucleus has been monitored in X-rays and other bands, this absence is not surprising because theoretical estimates suggest that such events are rare in any given galaxy, occurring perhaps only once every many tens of thousands or hundreds of thousands of years. Over the shorter span of modern observations, it is quite possible that no such event happens to occur. Instead, the Andromeda nucleus appears to show only weak variable emission associated with low-level accretion from more continuous gas sources. Even so, the same physical process of tidal disruption is expected to operate there in principle, shaping the long-term feeding of the black hole by sporadic injection of stellar debris. Gas clouds that approach the Andromeda black hole also face outcomes that depend on their trajectory and internal structure. A diffuse cloud that passes at a moderate distance may be sheared by differential gravity, elongated along its orbit, and eventually mixed into the existing hot flow without being strongly compressed. If a denser cloud falls in on a more radial path and comes close to the tidal radius appropriate for its size and density, it can be significantly distorted and partially stripped. Shocks can form when different parts of the cloud collide due to orbital crossing, heating the gas and causing it to radiate at optical, ultraviolet, or X-ray wavelengths, depending on the temperature reached. Some of the gas may be captured into bound orbits and over time join the accretion flow, while the rest continues outward. In the inner region where orbital speeds are high, even relatively small clouds can produce noticeable, though short-lived, increases in the local gas density and in the associated radiation if they are disrupted or compressed. The nuclear star cluster contributes to the gas supply in a more steady way through stellar mass loss. Many of its stars shed matter in the form of winds. In the outer parts of the cluster, these winds mix with the interstellar medium of the bulge, but closer to the center, some of the lost gas slows down and becomes part of the hot diffuse medium, that feeds the accretion flow. Stars on orbits that bring them closer to the black hole lose their gas into a region where gravity is stronger, making it more likely that a portion of this material will remain bound and drift inward. Over very long times, this continuous but gentle mass loss can provide a baseline level of fuel onto which rarer events, like partial or full disruptions of stars and dense clouds, add occasional bursts of extra material. The detailed fate of matter that passes near the last stable orbit differs from what happens at somewhat larger radii. Gas that has already cooled and settled into a rotating structure can maintain near circular motion down to that radius, but inside, circular orbits become unstable. Any gas that crosses this boundary begins a rapid inward plunge. As it falls, it may heat further due to compression and friction and radiate some of this energy, but in a radiatively inefficient flow, much of the energy is not emitted and instead remains in the gas as it approaches the event horizon. Once the gas crosses the horizon, it no longer interacts with the outside universe in a way that can be observed. Stars that somehow reach very small radii near radial paths without being fully disrupted at larger distances would also cross this threshold and be removed from the observable system. General relativistic calculations show that such direct plunges are possible for compact objects such as stellar mass black holes or neutron stars, which are dense enough to survive tidal forces to smaller radii than ordinary stars. Some of these compact remnants may spiral into the central black hole over long times due to emission of gravitational waves, contributing to its growth without producing strong electromagnetic signature. The rate at which these close interactions occur in the Andromeda nucleus depends on the density and velocity distribution of stars and compact objects in the central region. Models that use the observed properties of the nuclear star cluster and bulge suggest that full tidal disruptions of ordinary stars are rare, while partial stripping and close passages that heat and distort stars without completely destroying them may be more common. Such encounters can change the orbits and internal structures of the affected stars, but these subtle changes are difficult to detect at the distance of Andromeda gas clouds. Being more fragile and extended, can experience significant mass loss and structural changes at somewhat larger radii, helping to feed the inner hot flow even when complete disruptions do not occur. The general pattern that emerges from these considerations is that stars and gas approaching the Andromeda black hole face a sequence of possible outcomes set by how close they come to the center. At larger radius, they move as bound tracers of the central potential. At intermediate radius, they can be partially stripped, heated, and redirected, and at the smallest radius, they are either tidally destroyed or carried inward across the event horizon. Even though direct observations of these processes in the Andromeda nucleus are limited by distance and by the current low luminosity of the accretion flow, the same physical laws that are more clearly seen in other systems over long times, they govern how matter is removed from the nuclear region, how it contributes to the slow growth of the central black hole, and how the innermost environment of the Andromeda galaxy is shaped by rare, strong encounters superposed on a background of weaker, steady interaction. Understanding the central black hole in the Andromeda galaxy also means recognizing what present observations cannot yet resolve, in which properties remain uncertain. Dynamical models that fit stellar and gas motions give a mass for the black hole in the range of many tens or a few hundreds of millions of times the mass of the Sun. But this range still carries systematic uncertainty. Part of this uncertainty comes from how the mass of the surrounding stars is estimated. Astronomers must convert starlight into stellar mass using assumptions about the ages chemical composition, and typical masses of the stars in the bulge and nuclear cluster. Different reasonable choices for these assumptions change the inferred stellar mass, in turn alter how much additional mass must be assigned to the black hole to match the observed velocities. Another part of the uncertainty arises from the structure of stellar orbits. Models that allow more freedom in how orbits are arranged can sometimes fit a wider range of black hole masses, while models that impose stronger constraints on the orbital distribution give narrower mass ranges, but rely more heavily on those assumptions. As a result, the quoted mass of the Andromeda black hole is best seen as a carefully constrained estimate, with known margins rather than as a single exact value. The spin of the black hole is an even more open question. Spin affects the geometry of spacetime close to the event horizon, the location of the last stable circular orbits, and the maximum efficiency with which infalling matter can release energy as radiation. In bright active galactic nuclei, the spin of a black hole can sometimes be inferred by fitting the shapes of broadened spectral lines from the inner accretion disk, or by modeling other subtle relativistic signatures. In the Andromeda nucleus, the accretion flow is faint, and current instruments do not provide spectra with enough detail from the innermost region to extract such information. Without strong, well-resolved emission features from gas close to the black hole, the spin remains effectively unconstrained. Theoretical considerations suggest that past episodes of accretion in the history of any mergers with other black holes would have influenced the present spin, but these histories are not directly known. As a result, models of the inner flow near the Andromeda black hole often explore both low-spin and high-spin cases as possibilities, with observational data at present unable to distinguish between them. The detailed structure of the accretion flow also remains only partly constrained. The overall picture of a hot, low-density, radiatively inefficient flow is supported by the low luminosity of the nucleus and by the shape of its spectral energy distribution. But the exact geometry, density profile, temperature distribution, and strength of any outflows are not precisely measured. X-ray observations are limited by sensitivity and spatial resolution. Radio observations do not yet resolve the inner flow on scales comparable to the last stable orbits, and infrared data are dominated by starlight. Like the nuclear cluster, this means that many different internal configurations of the flow can be consistent with the same set of observed fluxes and spectra, provided they share the general property of low radiative efficiency. Questions remain about how much gas is lost to weak winds before reaching the event horizon, how magnetic fields are arranged within the flow, and how angular momentum is transported on the smallest scale. The behavior of the nucleus over long time scales is another area where knowledge is incomplete. Existing monitoring campaigns, especially in X-rays, cover only a small fraction of the time over which the black hole has existed. They show variability at low levels, but they cannot reveal whether the nucleus has undergone stronger outbursts in the more distant past, or whether it might experience higher accretion episodes in the future. Indirect clues from large-scale structures in the galaxy, such as faint shells or disturbances in the inner gas distribution, may hint at past periods of greater activity, but these interpretations are not yet firm. Without a long continuous record of nuclear behavior, the duty cycle of bright and faint phases for the Andromeda black hole remains an open question. Another limit comes from spatial resolution. Even with the sharpest current instruments, the region close to the event horizon of the Andromeda black hole is far too small to resolve directly. The nuclear star cluster and the apparent double nucleus have been mapped, but the inner accretion flow and the immediate surroundings of the event horizon remain below the resolution threshold. In the Milky Way, very long baseline radio interferometry has begun to probe structures on scales comparable to the event horizon of the central black hole, but doing the same for Andromeda is far harder because of its greater distance and lower flux. This difference means that while the general relativistic regime around the Andromeda black hole is described with confidence using theory, direct imaging of that region is beyond current capabilities. The precise three-dimensional distribution of stars in the nuclear cluster and their individual orbits also remain only partly known. Integrated light measurements reveal average velocities and dispersions, but they do not isolate single stars as is possible in the galactic center. As a result, the fine structure of the nuclear stellar system, including the possible presence of stellar disks, cusps, or cores on the smallest scales, is not fully mapped. These details could influence how often stars come close enough to the black hole to be tidally disrupted, and how efficiently stellar mass loss feeds the accretion flow. In the Andromeda nucleus, current data support a stable, dense nuclear cluster wrapped around the black hole, but the exact arrangement of orbits within this cluster remains a subject for further study with improved instruments. Gas dynamics near the nucleus face similar observational limits. While ionized and molecular gas motions have been measured on scales of many light years, probing the flow very close to the last stable orbits requires finer angular resolution and higher spectral sensitivity than are currently available. The degree to which gas follows simple circular rotation versus more complex patterns of inflow, outflow, or warping is for now known only in a broad sense. Small deviations from circular motion can change the inferred mass distribution if they are not properly accounted for, and disentangling these effects demands better data. Looking ahead, future observations and instruments are expected to improve many of these constraints. Larger ground-based telescopes with more advanced adaptive optics, next-generation space observatories with higher sensitivity in the infrared and X-ray bands, and more capable radio interferometers can all contribute to a sharper view of the Andromeda nucleus. Over longer baselines of time, continued monitoring will build a more complete record of variability, allowing the long-term behavior of the accretion flow to be better characterized. As these data accumulate, models of the Andromeda black hole will be refined, narrowing the allowed range of mass and placing new limits on spin, accretion geometry, and gas supply. For now, the central black hole in the Andromeda galaxy stands as a well-measured, but not completely characterized example of a supermassive black hole in a low-activity state. Its mass, its role in shaping the motions of nearby stars and gas, and its low present luminosity are all supported by multiple lines of evidence. While the fine details of its relativistic environment, spin, and accretion structure remain open topics that current observations only begin to outline, it remains a fascinating subject of study. Thank you for joining this exploration of the supermassive black hole at the heart of the Andromeda galaxy. If you enjoyed this calm journey to one of the universe's most extreme places, please support Sleepy Cosmic Lens by liking, subscribing, and sharing. Let us know in the comments what you find most intriguing about Andromeda's central engine, or what cosmic mystery you'd like us to explore next.